Greetings. So, welcome to today's class. So, a quick recap of where we were. So, we started looking at the state space representation. We looked at the state equation and the measurement equation. Then, the previous session, we were looking at the solution of ordinary differential equations. We looked at solution to first order ODEs with constant coefficients, and essentially we wanted to figure out what the solution would be even for a vector first order ODE, but homogeneous ODE, right? So that's where we were, and we saw that the solution would be of the form x of t equals e power at x of 0, right? So that's where we stopped. And we will continue from where we left off as far as the exercise is concerned. The exercise problem that we are looking at was to figure out how to calculate the e power at. So if we recall, e power at could be calculated by taking the Laplace inverse of si minus a, right? So that was the idea behind calculating e power at. So with this matrix A, so we will have si minus a to be equal to, if we consider a to be 1, 2, 0, 1, we will have s minus 1, minus 2, 0, and s minus 1, okay, as si minus a. Then what we will have is that, like, we will have the inverse of si minus a, which will be si minus a inverse, right? That's going to be, if you recall, the inverse of a matrix is going to be the adjoint matrix by the determinant, right? So the determinant of this is going to be s minus 1 whole square, right? So because we have a 0 element in the off diagonal entry, so this is going to be the determinant is going to be s minus 1 whole square. And what about the adjoint matrix? For a 2 by 2 matrix, calculating the adjoint is straightforward. We just swap the diagonal terms. But in this term, in this case, the diagonal terms are the same. So we will get s minus 1 and s minus 1. And what we do is that, like, we multiply the off diagonal terms by minus 1. All right. So let me repeat what I said. Please note that if we were to do the steps one by one, the adjoint of si minus a will be the transpose of the cofactor matrix, right? So how do we get the cofactor matrix? We eliminate the row and column to which an element belongs to and calculate the determinant of the remaining element. So suppose if we consider s minus 1, we eliminate the column and the row, right? The first column and the row, then the cofactor will be s minus 1 itself, right? So what is existing at the other, right? For 2 minus 2, it will be 0, right? For 0, it will be plus 2. Why? Because it is a sign. We need to essentially take the sign minus, okay? And then for s minus 1, once again, it will be s minus 1. Okay, in this particular case, please note that both these elements happen to be s minus 1. Okay, so but that need not be in general, right? So yeah, so please let's keep that in mind. So now if I transpose this matrix, you will get s minus 1, 2, 0, and s minus 1. So I hope it's clear how we got the adjoint matrix, right? So this is how we get the adjoint matrix. So if we have this adjoint matrix, now we take s minus 1 whole square inside. So we will immediately see that we will be left with 1 by s minus 1, 2 by s minus 1 whole square. We'll have 0, and then we will also have 1 by s minus 1, right? So these are the 4 elements of this matrix. So what we need to do if we want to essentially get e power at, we need to essentially have Laplace inverse of si minus a inverse. So if you take the Laplace inverse of si minus a inverse, we need to take the Laplace inverse of these 4 individual terms. If you look at the Laplace inverse of the 4 individual terms, let me go one step at a time. So we need to take Laplace inverse of 1 by s minus 1, the Laplace inverse of 2 by s minus 1 whole square, okay, and 0, Laplace inverse of 0 to 0, and then, like, we'll have Laplace inverse of 1 by s minus 1. Okay, so this is what we need to have. So if we do this, the Laplace inverse of s minus 1 will be e power t. Okay, Laplace inverse of 2 divided by s minus 1 whole squared will be 2t e power, right? How did we get this? We'll shortly discuss it. And then like Laplace inverse of s 1 by s minus 1 t e power t, right? How did we get 2t e power, 2t e power plus t? Sorry, not minus. Okay, yeah. So how do we get this? Using the complex differentiation theorem, right? So let's take a small digression. So let's say we consider f of t to be e power t, then f of s will be 1 by s minus 1. So if you recall the complex differentiation theorem, the Laplace of t times f of t will be equal to minus dfs dx, right? So this is something which we recall from a property of Laplace transform. So this will be minus, in this particular case, it will be minus d by df of 1 by s minus 1, which if you evaluate, you will get it as 1 by s minus 1 whole square. So you can immediately see that the Laplace inverse of 2 by s minus 1 whole square will be 2t e power t, right? So I hope it is clear how we got it, right? So this is the answer to the question on what will be e power at when we have a to be 1 to 0 and 1. Okay, so you can immediately see that this is not the answer, right? So we essentially looked at this, right? So we asked the question, hey, do we get the exponential of the matrix by taking the exponential of the individual elements? Certainly not, right? So you can immediately see that there is a difference, right, in between what we get by taking the exponential of each term and also following this process, right, where we have the what to say, exponential of by calculating the resultant matrix, right? So that's what we have done. Okay, so I hope this problem is clear to everyone, right? So how we get the uh, state transition matrix? Okay, please note that e power at is what is called as the state transition matrix. Okay, and this process, it's very important to calculate e power at because only if we know e power at we can find x of t, right? So by solving the state equation. All right. Okay. So now, yeah. So please stop me whenever there are any questions. Okay. So I'm just carrying on with the next example. So now, as the next exercise, let's consider the matrix which is diagonal in its structure. Okay. So let us say we consider a very simple matrix, 1 0 0 2. All right. So what happens in this case, right? If you want to find the e power at for this matrix. So if we want to find e power at for this matrix, so what we will have is the following. So we'll have the si minus a to be s minus 1, 0, 0, s minus 2. Then what will we have for si minus a inverse? For si minus a inverse, you'll have the inverse matrix as 1 divided by s minus 1 times s minus 2. Now the adjoint matrix is once again swapping the diagonal element. So now you can see that we have swapped the diagonal elements, right? And we essentially multiply the off diagonal elements by minus 1. But here in this case, the off diagonal elements are all 0, right? So they remain 0. So if we simplify this, we are going to get 1 by s minus 1, 0, 0, and 1 by s minus 2. Okay, so this is what we will have. So now, if we take the Laplace inverse of si minus a inverse, we observe something interesting, right? So what will we have? We will have the Laplace inverse of the 4 individual terms. And if we calculate the Laplace inverse in this particular case, we can immediately see that we get e power t 0, 0, e power 2t. So this is a very, very special case, right? So if you have a diagonal matrix, what happens is that the calculation of e power at becomes very simple. The e power at matrix will also be a diagonal matrix whose diagonal term will be exponential function whose exponents are the diagonal entries themselves. So you can see that the diagonal entries are e power at and e power t and e power 2t, and they are nothing but the elements, right, that appear in the diagonal as the diagonal entries in the matrix A, right? So the diagonal entries are 1 and 2. So we get e power t and e power 2t, right? So this is a very special case. That is like when we have the matrix to be a diagonal matrix, okay, the exponential of the diagonal matrix will be also a diagonal matrix with the entries being the exponentials of the individual diagonal elements, okay, of the original matrix. Okay, so this is a special result only for a diagonal matrix. Okay, so please remember this. Okay, so that is why many times, if possible, we would like to work with a diagonal state matrix. Okay, because the calculation of e power at becomes very straightforward, right? So we are given a diagonal state matrix, e power at calculation becomes much simpler due to this result, right? So that is a big advantage for it. All right. So at this point, for those who are mathematically inclined, okay, who want to essentially find more about this, if you want to learn more methods to essentially on the process of calculating the exponentials of a matrix, you can look at this reference. If you go to Google and type this title, you will get it. Okay, so the article is titled as 19 dubious ways to compute the exponential of a matrix. Okay, so that's the title of the paper. So you could look at, all right, if you are interested. So this is a nice article, and you could look at it if you are interested in learning more about this topic. All right. So we have used this method of using the resolvent matrix for our computation. So essentially, we take the Laplace inverse of the resolvent matrix and we get the state transition. Okay, please note that the resolvent matrix is Si minus A inverse. We take the Laplace inverse of that and we get the state transition matrix e power t. All right. Okay. Fine. Okay. So now that we have looked at the homogeneous or the solution to the homogeneous part, right, of the state equation, we need to look at what happens with the general state equation, right? So now let us consider the complete state equation. So what do I mean by the complete state equation? That is, we are considering x dot e equal to axt plus but. Okay. So we can immediately observe that we are going to consider this forcing term, right? So now we can immediately observe that the ODE has become an inhomogeneous ODE, right? So we have this forcing term BU coming into play. So let's try to get the solution for this equation. So what we do is that, like, we take the Laplace transform on both sides of this equation. Okay, so if we take the Laplace transform, what will happen is that we will get a Laplace of x dot 2 equal to s times x of s minus x0 will be equal to a times x of s plus b times u of s. Okay. Then what happens is that, like, if we simplify this by collecting the terms of x of s, you have si minus a capital X of s, right? That's going to be equal to x0 plus b times u of s. Okay, so that's what we have. So now if we take the inverse of this matrix with si minus a, we are going to get si minus a inverse x0 okay, plus Si minus A inverse B times U of t. Okay, so that's what we have. I hope it's clear. Please stop me if there is any question on any step. Okay. So now, if you want to calculate x of t, what we do is that we take the inverse Laplace. So if we take the inverse Laplace transform on both sides, what do we get? Take the inverse Laplace transform on both sides, we will get x of t, right? So we will have x of t to be equal to e power at x0. That's something which we know, right, from our discussion. Now, what happens to this inhomogeneity, right? So please note that here we are going to use the convolution integral, right? So if you recall, one of the properties of the Laplace transform is that, like, let's say we have two functions in the S domain, right? And we multiply them, and we want to take the product. We want to take the Laplace inverse of the product in the time domain. The result will be what is called as a convolution integral. Okay, so the convolution integral is this. It will be f of t minus tau g tau d tau. Okay, and integrated from 0 to t. All right, so this is the convolution integral. Okay, so where capital F of s is the Laplace of small f of t, and capital G of s is the Laplace of small g of t. Okay, so those are the that's the one of the properties, okay, of the Laplace transform, right? So that's something which we are aware of. So we are going to use it here. So if you use it here, so now in this case, f of t is going to be e power at. Okay, so because taking the Laplace of that will give us Si minus A inverse. So e power, we'll have e power a t minus tau. So wherever there is t, we put t minus tau for the first function. The second function is b times u tau. Okay, because u is the second function. So in this case, f of t is going to be e power at. Okay, g of t is going to be ut. Okay, so that is what is going to be, of course, to be very precise, it's going to be b times ut. But b is anyway a constant vector. Okay, so yeah, we will have b times ut. Okay, as the result. Okay, so this is what we will have, like as the what is it? The state, okay, when we apply the inverse Laplace transform. So you can immediately observe that there is an extra term, right? So previously we had this e power at x0. Now we have this term due to the input, right, which appears additionally. So this is the solution to the state equation. Okay, so essentially, if we look at the solution to the state equation, x dot t equals axt plus dut, what we have derived is the solution to the state equation. Okay, so we have two components. One is due to the initial state, and another is what is due to the input that is provided. Okay, and please note that the output y of t is for the single input, single output system, c dot x of t plus d times u of t. Okay, so if we use that, so the output is going to be, if we substitute for x of t, we will get c dot e power at x0. Okay, that is one term, plus c dot integral 0 to t e power a t minus tau b u tau d tau. Okay, that is the next term, plus d times ut. Okay, so once again, we can see that there is a component due to the initial condition and component due to the input. So as we know, the first component corresponds to free response, Okay, the second component corresponds to the first response, right? So this is something which we have already looked at. So if you look at the transfer function representation, as we have already discussed, by and large, we are going to be interested mainly on the what to say, free response, right? So, sorry, if you look at the transfer function representation, we will be mainly focusing on the first response, right? Why? Because we consider all the initial conditions to be zero, right, when we derive the transfer function. On the other hand, if we consider the state space representation, we will consider both free response and the forced response. Okay, so that is an important change, right? So, in a certain sense, the state space representation naturally takes into account, like the response due to the non-zero initial condition, right? So we can analyze both. Right? So of course we can even get the free response using the Laplace transform method. But as we can see, this naturally comes into play. All right, when we are dealing with the okay. Okay, if not, let's continue. So we have looked at the results for CISO. In fact, one of the advantages of the state space representation is that when compared to the what to say, a transfer function representation, the analysis of memo systems, right, happens more naturally, right, in the case of state space representation. So, if you consider a memo system, and if we want to look at the transfer function representation, we will have a transfer function matrix because now we have more than one input and more than one output, right? So we will get what is called as a transfer function matrix. So this is a transfer function matrix. Okay. In the case of a memo system, this comes in naturally. Okay. So that is a big advantage, like as far as our analysis is concerned. So now the question is that, like, how do we what to say correlate the transfer function matrix along with the state space representation for the linear system. So if we recall, we wrote down the state space representation for a multi-input, multi-output system, right? So the state equation could be written as AXT plus DUT. Of course, now U is a vector, and the output is also a vector, y of t. That could be written as CXT plus DU, right? So now A, B, C, D are matrices of appropriate dimension. Okay, we can essentially observe that the realization for this system is the set ABC. Okay, so now, in fact, if we take the Laplace transform, okay, I'm going to leave this as an exercise to you. Okay, take the Laplace transform and show that the Planck transfer function now can be related to the realization as C times Si minus A inverse B plus D. Okay, so it is something very similar, right, to what we had for the CISO system, right? So it is essentially you just need to take the Laplace transform, apply zero initial state, and then you will get the answer. All right, so please try it out as an exercise. So for a CISO system, we have C dot Si minus A inverse B plus D. Now these are all like multi-input, multi-output systems. So we will have this particular relationship, okay, between the Planck transfer function matrix, okay, and the state space realization. Okay, similar to the CISO case, if we integrate for the state equation, we are going to get x of t to be equal to e power at x0 plus integral 0 to t e power a t minus tau b u tau d tau. Yeah, so only as you can see now, the difference is the fact that we have multiple inputs and there is an input matrix. Okay, so those are some key differences. Similarly, if we look at the output y of t, the output vector, which is cx plus du, so we will have c e power at x of 0 plus t times 0 to t e power a t minus tau b u tau d tau, okay, plus du. Okay, so this will be the output. Okay, so this will be the solution to the state equation and the output equation. Okay, as far as the memo system. Okay. Okay. So we will be using these as we go along. Okay, so we'll find them to be pretty useful, right? And essentially, like it's what to say, this is like something which can be which will be analyzed further, right? So as we go along in our discussion on state-based representation. Right? Okay. So now what I'm going to do is going to do one example, right, through which I'm going to demonstrate, some key points, okay, in the what to say, in the process of writing the state space, right? Essentially, consider, uh, let's say we consider a standard second order LTA system whose governing equation is going to be y double dot t plus a y dot t plus dy of t, okay, that's equal to some u dot of t plus t times u of t. Okay, where a, b, c are some real scalars. Okay, so a, b, c are all some real numbers, real value scalars. Okay, now we can immediately observe. By now, I'm sure all of us are familiar with this process. We can immediately get the transfer function to be s plus c divided by s squared plus as plus b, right? So by taking the Laplace transform on both sides, uh, applying zero initial conditions and what to say, cross multiplying, we get this as the transfer function, right? So now we can observe that the transfer function is the same for all of us, right? So this is a very important point which we will discuss going into the next few classes also. Uh, if we are given a dynamic system and whose governing equation is also given to us, the transfer function that we derive, right, will be the same, okay, for all of us. That means that the transfer function is unique, okay, for a given system. However, the state space representation is not. All right. So we'll also see why it is not and how it is useful to. Okay? So let us go further in our analysis. So in this particular case, we observe that the values of n and m are 2 and 1 respectively. Okay, so that is the first observation I want us to do. Why is this important? Please note that in the transfer function representation, we need to choose as many state variables as the order of the system. Since the order of the system is 2, let us choose the two state variables x1 and x2 as y and y dot. Okay, and let's see whether we are able to write the governing equation in the state space representation. Okay, let's make an attempt. So if we have this, we will immediately see that x1 dot will be equal to y dot, okay, and that's going to be equal to x2. Okay, this is a very straightforward equation to write. Correct? Yeah. So now let's come to x2 dot. What will be x2 dot? X2 dot will be y double dot. Okay. Now y double dot is going to be from the governing equation. It's going to be minus dy minus ay dot plus u dot plus cut. Right? So this can be written as minus bx1t minus ax2t plus u dot t plus cut. Is it not this one? We can write. Okay. Now, if you want to group them into the state equation and the measurement equation, what is that we use? So, if you want to group them as x1 dot t and x2 dot t, what will we have? Okay. So, we will observe, let me write down the equation group together, then we will make a few key observations. So, x1 dot t will be something times x1, x2 plus something times u dot t plus something times u. Okay. So if we write this, we will immediately see that this will be, this will be 0, 1, this is 0, this is 0, this is minus b, this is minus a, this will be 1, this will be c. Okay. So we can see that if we multiply through, we get the two state equations. Right? So this is the standard process of writing the state equation, right? But however, we face a problem now, right? So what is the problem? Please note that the state equation in general should be of this form, right? Considering a SISO system, as in this case, it should be of the form axt plus but. Okay, but however, we are having a u dot term. What do we do with that? Right? Because you can immediately observe that this is not in the standard form at all, right? So there's a u dot term which comes into play, and consequently, like this doesn't fit the standard form, right? In fact, if you say on the other hand, hey, combine these two terms, write them as this in this way, right? 0, 0, 0, 1, c u dot t u, right? So that like you will sort of have a compact notation. But we get into an issue here also, right? Because you see that this now, if you call it as a modified input vector, this becomes a vector, right? But we are having a SISO system, right? So we can't arbitrarily do things like this, right? So essentially, that's something we need to look at, right? So obviously, the choice of the state variables that we have made, right? So x1 equals y and x2 equals y dot is dot appropriate, right, in this particular case. So what do we do, right? So in fact, this is an interesting problem, right? So because in the state space representation, one of the main challenges is to essentially choose the state variables and select them so that like we are able to what to say sort of express them in the state space representation and write the equations, right? But here in this example, we are getting a u dot, right, which is not part of the state space representation. So what we do is that like we essentially redo the exercise, okay, by having a having another choice of state variables. Okay, so let's do it. Right. So let's say we choose x1t to be equal to y of t, x2t to be equal to y dot of t minus ut. Okay. So let's say these are the two state variables. All right. Okay. So now what will happen? X1 dot. Of course, the question that would immediately come to our mind is that, hey, how did we choose this x2, right? We will answer them as we progress further, right? So see, if there is no method to choosing this x, right, we would be sort of like doing these things by trial and error, right? Not quite so. Okay, so there is some method behind the choice of these state variables. We will see how, right, as we go along. Okay. Let's just do this exercise, and then like in the future classes, we will learn how do we write it in these forms. Okay. So let's say we take the first derivative. As always, like we need to choose as many state variables as the order of the system. And then we need to take the first derivative of each state variable, right? That's what we are doing. So x1 dot is y dot, but y dot from the second equation is going to be x2 plus u, right? How did we get this? We got it from the second equation, right? So this equation, we can immediately see that if we rearrange the term, y dot t will be equal to x2t plus u of t. Okay, so that's what we would have. So then what do? We need to take x2 dot, right? X2 dot is going to be equal to, now please note that it's going to be y double dot minus u dot t, right? So we are going to have some extra terms, right? So y dot, sorry, y double dot will be minus dx1. I'm just taking from here, right? We have already got the expression for y double dot, so I'm just taking from there. So it will be minus dx1 minus ax2 plus u dot of t plus cut, and we have a minus u dot t. How did we get the minus u dot t? Because our definition of x2 has a u, right? So if I differentiate x2, I get a u minus u dot. So now you can see that the u dots cancel off, right? And we have left with a simpler thing to solve. All right. But however, of course. Oh, okay. I think I did a mistake here. Sorry about that. Okay, let me erase this. Right. So I have to be a little bit more careful. So please let's go from the beginning. Right. So y double dot t. If I go here, we need to go to the governing equation. Okay. So y double dot t will be. I have take from here. Sorry about that. Okay, I think I substituted from the wrong equation. Okay, I need to substitute from here. So if you do it very, very carefully, let's do step by step. We will have minus dyt minus a y dot t, okay, uh, and then plus u dot t minus, sorry, plus cut, and then finally a minus u dot, right? Which comes out of a differentiating. Of course, u dot and u dot cancel off. But now we need to substitute for y dot, right? So that's another step we need to do, right? We have a y dot here, right? So consequently, what will happen is the following: x2 dot will be equal to minus b times y is x1. Y dot is going to be equal to x2 plus u, right? Plus c times u. So what will happen to x2 dot? You have minus bx1 t minus ax2 plus, yeah, right? So there is a difference here. So if we collect the equation, the two state equations, we get in the we get a form of the vector ODE. So what will happen to x1 dot x2 dot? Let's now group them. Now you can see that the equation for x2 dot does not contain u dot, right? So it contains only the state vector and the input, right? So that's what we want, right? So if we write this, x1 dot is x2 plus u, so we will have 0, 1, and then we'll have a 1 here also, right? And then x2 dot, we will have minus bx1 minus ax2 plus c minus a u of t. All right, so we have this to be our input vector, okay, 1 and c minus. And what about the output equation? Y of t will be equal to anyway x1 of t, and that can be obtained by taking the dot product of 1, 0 with the state vector, right? x1 and x2. Okay, so this is what you would have. All right. So you can see that now we have put the what I say governing equations in our standard state space form. But however, like we adopted a slightly different process to get there, right? So choice of state variables was different, right? But once again, like we essentially get this question, right? So how do we do this in general, right? So if you have to do this sort of like what looks like a trial and error process, then this becomes intractable, right? So a question that we will answer as we go along is that like how do we write standard canonical, what are called canonical state space of dynamic systems. Okay, so this is something we will learn as we go along. So we will see that what we have done belongs to one such representation. But that's something which we will figure out. Okay, as we go on. Okay, like please note that the transfer function representation is unique. Okay, but the state space representation is non-unique. Okay, so that's something which is an important concept, right? That we need to understand. And why is the state space representation non-unique? Can we show it by some means? Like we will do it in the next class. But is it a good thing or a bad thing? It depends. Once again. So we will see that we are going to use the fact that the state space representation is non-unique to our advantage in many problems. Okay, so we can essentially transfer or transform the state space representation using some tools to get a very simple set of equations. Okay, that we can work with. All right. We will learn in the next class. To teach in today's class, I think there was a disruption in between in the internet connection. Can you hear me? Yeah.
No, sir. I think in the middle of class we had small distraction, a few seconds only.
What about now?
Now it's okay.
Now it's okay. So yeah. So why it is non-unique and how we can utilize it, utilize that attribute is something we will look at in the next class. So these are the concepts I wanted to essentially touch upon in today's class. Are there any questions on that? Okay. So if there are no questions, I will stop today's session here and we will continue in the next